Hi, welcome back, and welcome to the second part, the second video for this talk. So in this video, I am going to present the main result and give some ideas as to why um, the proof works. And so the modules that we use for the theorem are not going to be the modules that we learned in the previous video. They're going to be a slight modification to those modules, and I call them the modified Alexander model, Alexander modules. They're closely associated to the modules we learned in the previous video, and they use those modules sort of as a jumping off point for their definition. So to get us started, what I'm going to do is I'm going to remind us of the classical Fox-Milnor theorem, and I've changed this up just a little bit. In the previous video, I said if K is a slice knot, and then said more generally, if K is 0.5 solvable, this theorem holds. But here I'm stating this as if K is one solvable, then as Alexander polynomial factors as F bar. So I'm using one solvable here because the main result that is coming later in this video is takes as its premise an integer solvable knot, not half integer. I would like to see if we can extend this to half integer, but at this moment in time, that's not what we have. So if K is one solvable, then as Alexander polynomial factors is F bar. So if we're thinking about ways to extend this, one way we may have in mind is to say that if K is an n+1 solvable knot, then it's nth order Alexander polynomial factors in this Fox-Milnor style. As I mentioned at the beginning of the video, this isn't exactly true. And what I want to do now is I want to explain the obstruction to getting this sort of result on the higher order modules instead of on the new modules that we're going to be looking at later. So to do this, let's take a look into some aspects as to how we prove the Fox-Milnor condition in the classical case. So the idea is that if I have, say, the zero surgery of a knot, and here I'm going to use a zero surgery for a couple of reasons. Topologically, it's more intuitive to use, as you'll see from this example. Algebraically, it's easier to use, and it makes our result later look a little cleaner, a little nicer. So from here on out, we're going to use the zero surgery instead of the knot complement. So if I have the infinite cyclic cover of my zero surgery, I note that the deck group for this cover is Z, which is the first homology of our zero surgery. It is also the first homology of any n solution this zero surgery may bound, because the first condition for the definition to be an n solution is to have this isomorphism on H1. So that means that Z, or the first homology of M, is a coefficient system for M that extends over any given n solution. So in particular, like topologically, what this looks like is that if I take the infinite cyclic cover for W, so in W here is an n solution. So if I take the Z cover for W, its boundary is going to be the infinite cyclic cover of the zero surgery of the knot, the infinite cyclic cover of M. So here what we have is, so here what we can define is an Alexander module for W and an Alexander module for M, such that topological inclusion induces a homomorphism on the Alexander modules, because they're both defined with respect to the same coefficient group, or coefficient ring in this case. And so in the method of proving the classical Fox-Milnor theorem, the factorization is realized through taking the order of the kernel of this homomorphism. So the factorization is the order of P, where P is the kernel of this induced map, times the involution of the order of P. This breaks down when we try to move to the higher order covers, because in general, Rn is not a right Z pi 1 W module, meaning that our coefficients for our higher order modules don't necessarily extend over any given n solution. And if I don't have that extension, inclusion can't induce a homomorphism on the modules because the modules just exist over two completely different rings. And if I don't have an induced map, I can't get a kernel. And if I don't have a kernel, I can't get that factorization. So this is the big obstruction to getting the Fox-Milnor theorem for the higher order cases. This is a lesson I learned a long time ago, a lesson I learned the hard way. But there is a fix, there is a workaround. And that workaround is to slightly change the Alexander modules. So we do this through the use of what I've been calling a modification. A modification for K, this is essentially going to be a modification for the coefficient systems for our zero surgery. So if I have a collection, it's a collection of subgroups of our coefficient groups gamma n called that we call Pn. The entire collection we'll call P. And it's a collection such that for each n and each quotient, which we'll call gamma np, we have that these quotients are PTFA, or in particular, the group ring is an Ore domain. And two, we have a surjection from gamma np to z that commutes with the projection of gamma n to gamma np. So the second condition, what I mean by this is we know that there's a surjection, a natural surjection from gamma n to z. And I want that surjection to be the same thing that as if I composed with gamma np and then compose that with psi n, I would get that surjection. So what point 2 actually gives us is that when n is 0, gamma naught and gamma naught p actually align. They are the exact same group. So even though we're doing these modifications, if I take the 0th module, so when n is 0, I'm going to get the classical Alexander module back. So that's what the second point is giving us. So again, z gamma np is an Ore domain, and we have this rejection on the z, so that allows us to find these PIDs, similar to how we did in the case of the higher order modules. And this allows us to define the modified Alexander modules to be the twisted homology modules with these modified coefficient rings. And the modified Alexander polynomial will just be the order of the modified modules. So here, these modified modules have, pretty much the exact same properties as the higher order modules. They're finitely presented. They're torsion. So their orders are never going to be 0. The simplest you can get is 1. In fact, something I didn't mention in the previous video, might as well mention now. If you have a knot with a non-trivial Alexander polynomial, then all of its higher order modules are non-trivial. That same fact holds for the modified modules as well. So we're not defining something that just, could be trivial ad infinitum. These things are non-trivial if the classical Alexander module is non-trivial. So the theorem that we can actually formulate is if K is an n+1 solvable knot, then there exists a modification for K such that the corresponding nth order modified Alexander polynomial of the zero surgery factors in the Fox-Milnor style. Okay. So now let's look at the ingredients that make this theorem happen, or moreover, why modifying allows us to get the factorization, whereas not modifying doesn't allow us to get the factorization. So to do this, I'm going to actually prove the factorization first in a simpler case. Not an easy case, mind you, but a simpler case. And this is going to be the case where I take my coefficient groups from the n solution. So if I have an n+1 solvable knot and an n+1 solution W, I'm going to get these coefficient groups gamma and W. These are going to be the quotients of the fundamental group of W by the n+1 irrational derived subgroup. Inclusion of MK in the W induces a gamma and W coefficient system on our zero surgery MK. So that just, you take the composition of inclusion and then projection, and that's going to give gamma and W as a coefficient group for the zero surgery. This coefficient group is PTFA. We mentioned this earlier, actually, that we have this isomorphism with Z. This gives us an epimorphism onto Z, so we can define PID R and W in the exact same way we did for the pi order modules and the modified modules. Okay. So now, if I look at the corresponding twisted modules, these are finitely presented in torsion, so they're going to have a non-trivial or non-zero Alexander polynomial. These polynomials actually satisfy the Fox-Milnor factorization. And they satisfy the factorization because the coefficient system that we're using extends over the n+1 solution. And it extends over the n+1 solution because they came from the n+1 solution. So this is sort of fixing the problem by, taking a group that extends because that's where it came from. So this is what I meant by this is an easier case to work in. So here the factorization actually obeys another property that we saw before with the Fox-Milnor case, that it's realized by taking the order of P, where P is the kernel of this induced homomorphism. And I believe I should have this saying Pn because we want this n to depend on this n, but it's fine. Okay. So what I want to do is I want to find a modification for my knot that in some sense is compatible with this coefficient system that I have on MK that allows us to get this this factorization. Sorry. And I'm going to do it in such a way such that I can pull that factorization back from one coefficient ring to the other coefficient ring. So the way we define this modification is actually by realizing that our map from pi1 of mk to gamma nw factors through the gamma n's that we defined previously. So the modification I'm going to take is just going to be the kernel of the homomorphism from gamma n to gamma nw. I'm going to call these kernels Pn, and that's going to define my modification. So to explain why this modification works, and so actually before I get into that, I want to point out something that's maybe a little strange. So here we have a group that can be identified with a subgroup of the coefficient group we use to get the factorization. That means when I go through the motions, get my PID, my coefficient ring and all that, this is going to be isomorphic to a subring of the PID we get from gamma nw. In fact, there's going to be an embedding that sends the smaller ring into the bigger ring. So what we're doing is taking a factorization in the bigger ring and pulling it back to the smaller ring. And it's not at all obvious that we can do that. We definitely cannot do this in every case. But it turns out that here there's just enough structure that we get from the topology that allows us to pull back that factorization. And so the topological observation that sort of kicks this all off is understanding what the cover looks like. So let MK tilde be the regular gamma NP cover of MK, and W tilde is going to be the regular gamma NW cover of W. So the gamma NW cover of MK is going to be the boundary of W tilde, and that's just going to be this disjoint union of MK tilde, and this is going to be indexed by the index of gamma NP and gamma NW. This is a bit of an abusive notation because gamma NP is not a subgroup of gamma NW, but here we're just going to take it to be. It makes the notation a little bit cleaner. So visually, what this gives us is a bunch of path components, each homeomorphic to MK tilde. And when I act on it by elements of gamma NP, as it lives in gamma NW, the action on each component is just going to be the same det group action we would have if we just had MK tilde as a cover of MK. If I act on it by an element that's not in gamma NP, what it's going to do is going to permute the path components as well as act on them in the gamma NP style. So this gives us maybe our first insight into maybe how we can pull this factorization back, because all the meaningful action that we see here appears to come from gamma NP. So when we extend this to the Alexander module, it's not too hard to believe that the interesting actions that we get from the Alexander module with coefficients in R and W are going to come from the subring R and P. And so maybe, just maybe, the factorization pulls back if the rest of R and W, doesn't have anything to say about it. But to realize this intuition, we have to make a couple of observations. So first, it's something that I've already mentioned, that the inclusion of gamma NP into gamma NW, this monomorphism, this induces a ring embedding on our PIDs, RNP into RNW, and I'm going to call these embeddings epsilon sub n. These embeddings commute with the involution, and they're going to extend to an embedding on their skew field of fractions. The second thing to observe is this is really just a consequence of what we saw on the previous slide, is that as an abelian group, and moreover as an RNP module, the homology groups H1, MK of R and W are isomorphic to this direct sum of homology modules. So this isn't anything special. This is just saying that the homology of a disjoint union is isomorphic to the direct sum of the homologies of the path components. But what is kind of surprising is that if I view this now as an R and W module, this twisted homology group with coefficients in R and W, this which decomposes this way, is actually generated by a single summand. So we just need one of these summands to generate the entire module. So given that, consider an RNP module homomorphism. So we're viewing these as RNP modules now. We'll review this module homomorphism sigma that takes one of the summands and sends it to, one of the copies of the summands and sends it into the direct sum. And what it's going to do is it's going to take a designated summand here on the right, and for every element, it's just going to send it to itself as it lives in that distinguished summand. We have the property now that if I tensor with R and W, what I end up getting is an isomorphism. And because I get this isomorphism, this tells me that if I look at the image of my modified Alexander polynomial under this embedding, epsilon n, I'm going to get the polynomial for coefficients in R and W. So we have this compatibility with respect to the embedding. Moreover, here, I guess I've been mixing up notations when I'm writing this down. These should just be P's instead of PNs. But if I take this new module P hat, the submodule P hat to be the kernel of this composition of homomorphisms. So what I'm doing here, and I'm viewing again everything as R and P modules. So what I'm doing here is I'm using that sigma to bring H1 MKR and P into H1 MKR and W, and then including in the H1W R and W. This has the property that, again, if I tensor with R and W, I'm going to get that same module or the same submodule P that we saw previously when we did the Fox-Milnor condition with R and W coefficients. So what that tells me is that if I embed the order of P hat, if I look at the image of the order of P hat under this embedding, I get the order of P. So these two ingredients together combine to give us the factorization. And when I first wrote this slide, I was going to go into detail about, what's going on with this equation and why that gives us this thing down here. I don't think I really have the time or even the energy, or maybe you don't even have the energy to follow through this equation. But those two ingredients combine together to allow us to pull back the factorization. And the main idea is that under this embedding, we get that this is equal to, and sort of this weird group we defined in the last video that determines the indeterminacy of our polynomials, that under the embedding, this is equal to some unit times something in the image of that embedding, which means this unit is in the image of the embedding. And we can use some algebra to show that when I pull that unit back, so if I take it, its image, so epsilon n inverse of u double prime, this is actually going to be a unit in R and P as well. And so that's how we get the factorization in the modified modules. from pulling it back from these modules defined over R and W. So before I end the video, there are a couple things that I want to say. So first, it's really difficult to factor in these rings. Skew polynomial rings are a beast. Factorization is very difficult, even when you know that there's a factor there. And in some polynomials I worked with, I know there's a certain factor there. Finding it is almost impossible. So what I would like to do, or what I would like to see done, is to develop a systematic way to factor these polynomials. One promising situation in which this is possible, or might be possible, is in the first order case, where the ring structure is simpler and essentially just depends on the Alexander module itself. So if you know the Alexander module, the structure of the Alexander module of a knot, you know the structure of Rn, and by extension, you know the structure of Rnp, because Rnp is going to depend on just quotienting out by some submodule of the classical Alexander module. If this is unfeasible or intractable or some other word that means you can't do it, I would like to find another way to detect this factorization, or another invariant that is easier to compute, that also detects this factorization. The second thing I want to say is that some upcoming work extends recent results of Friedel and Powell. So in 2019, they showed that if K is homotopy ribbon concordant to J, then the Alexander polynomial of J divides the Alexander polynomial of K. Some upcoming work shows that this result extends very naturally in the context of the modified higher order polynomials. In fact, the notion of the modified modules and modified polynomials have their root in understanding homotopy ribbon knots. So this extends very naturally in this case. And in terms of computable obstructions, this shows more promise, as there's a numerical obstruction we can potentially get out of this, rather than a polynomial obstruction that will take a lifetime to actually factor. So the modified modules have more purpose than just what you've seen in this video. And so I'm looking forward to seeing what else they can show us about knots and the world of concordance. Okay, so that's it for me. That's it for this video. I hope that you enjoyed these two videos. I'm looking forward to see if you have any questions. So thanks.